Hello, myself Dr. Shaila Dinkar Apte. Let us continue with Signals and Systems Chapter 3. This is also useful for digital signal processing students. So, we are dealing with properties of continuous time and discrete time systems. So, here we go. Following are the learning objectives for today's lecture. Invertibility of the system, stability of the system, what we call it as BIBO stability, bounded input, bounded output stability, systems as interconnected operators, and series and parallel interconnections. So, we'll start with invertibility. So, what is invertibility? Let us understand the meaning of the invertibility. Suppose we consider the system represented by the block as capital H, then there must exist the system called as H inverse. It is not the inverse, it is just denoted as inverse. So, H multiplied by H rather convolved with H inverse must be equal to 1. So, given the system H, if I convert xt into yt, I must have H inverse x, H inverse t that will convert this yt into xt. So, I must be in a position to revert back to the original signal xt. If it exists, then we say that the system is invertible. What are the requirements of invertibility? The requirements will say that there must be exactly one-to-one correspondence between input and output of the system. If there is one-to-many correspondence, then I cannot recover the signal exactly. So, in that case, the corresponding inverse system, we say that it does not exist. H inverse is not the reciprocal operator, but it is the symbol used to indicate the inverse, as I already told you. Now consider some CT systems, continuous time systems. Let us say that yt is represented as cos of x of t. Okay. Now how to recover xt? Xt will be recovered as cos inverse y. But for every plus or minus 2n pi, the cos value will be same. So xt will be recovered as cos inverse of yt plus or minus 2n pi. So here in this case, there is one to many correspondence. The system is not invertible at all. It is not one to one correspondence, it is one to many correspondence. We have seen that if the sinusoid of 10 hertz is sampled with the sampling frequency of 7.5 hertz, this we saw in the previous lectures, we recover it as 2.5 hertz because of the aliasing. So, in this case the system is not invertible. So, you understand that there is essentially the requirement that the system must be invertible. Otherwise, when we sample it and if we try to recover it back, if we recover it as something else, then it is of no use at all. So, the system will have to be invertible when you are sampling, right? Now consider the system yt is equal to integration minus infinity to t by 4 x of tau d tau. So how to recover x of t by 4? X of t by 4 will be recovered as dt of yt. So this is definitely invertible. Now consider some dt systems. Yn is equal to sine of xn. Here again xn will be recovered as sine inverse yn plus or minus half. Why half? Because half is the maximum digital frequency as we have seen. So in this case again there is one to many correspondence and the system is not invertible at all. Consider yn is equal to xn into un. Now this system is invertible. How I can recover xn? This un, what is un? Un is summation n varying from 0 to infinity x of means it is un is equal, un exists only for n equal to 0 to infinity, right. So how I write yn? See, suppose yn is written as summation m varying from 0 to infinity x of 3 into x of m. Now if I expand this, I can write it as 3xn plus 3xm means it is x of 0 plus m is equal to 1 to infinity 3 into xm. So how I can recover xn back? Xn is equal to 1/3 of yn minus summation m varying from 1 to infinity 3 into xm. After expanding you will get this. So the system is invertible. Now consider this system. Xn is yn is equal to xn square. Let what will be xn? I can recover it as plus or minus under root of yn. So this plus or minus indicates that there are two values of xn, those are obtained. So in this case it is not invertible. In this case the system is invertible. Yt is integration t minus 3 to t x tau deta. So I will write xt minus x of t minus 3 is equal to d dt of yt. So I can recover xt from yt. So this system is invertible. Now let us consider the physical significance of invertibility. Now let us say that we are using some operation to remove the noise from the signal. And if this particular system is not invertible, even if the noise is removed, we will not be getting the system back, that is the signal back. So in this case it is of no use. If we process the signal to extract some features of for recognition, so let us say that we are dealing with speech recognition. We have extracted some features and we are processing these features further to recognize whether it is a particular word or not. Now in this case we are not interested in getting the signal back. So in this case the system may be non-invertible. That will be no, you won't have any objection if the system is non-invertible, because you are just extracting the features and using it. So in this case there is no requirement that the system will be invertible. Now suppose we want to have error-free transmission from the transmitter to receiver. What we do is we design the equalizer at the transmitter end. How the equalizer is designed? Equalizer will have the characteristics which are same as the inverse characteristics of the channel. So you are compensating for the channel. So this is the use of the invertible system. Then we go to stability. The system is required to be stable, obviously, because we want that the output of the system should be finite, it should be discrete, right? It should not go to infinity. So if the output becomes unbounded, system becomes unstable. So the system output should not increase beyond the bounds. So it should have some bounds. Then we say that the system is stable. So the system must be stable for all inputs. So for all bounded inputs, the output should generate the bounded value. So types of the responses. When we analyze the system, we extract the responses of the system as either zero state response and zero input response. Zero state response means there are no initial conditions. So under no initial conditions, we find the output of the system, that is called as zero state response. And when we apply the input, when we apply the zero input and the initial conditions are not zero, initial conditions are there, and we are calculating the output because of the initial conditions only. The output in this case will be considered as zero. In this case it is called as zero input response. So when we are calculating zero state response, the initial state will be made zero, and when we consider zero input response, the input to the system will be treated as zero. So whatever the initial conditions are, because of the initial conditions, what is the output that is developed, that we try to analyze. Now let us define what is BIBO stability, bounded input, bounded output. That is the means long form of BIBO. An arbitrary relaxed system. Relaxed system means there are no initial conditions. Any relaxed system is said to be bounded input, bounded output stable, that is BIBO stable, if and only if its output is bounded for every bounded input. So let us assume that the input is bounded, then if the output is also bounded for all values of t, then we say that system is BIBO stable. Similarly, for discrete time systems also, the similar condition will be holding good. Now consider one example. Let us consider the system yt given by integration minus infinity to t x of tau d tau. Now if x of tau is limited, if x of tau is x of t always mod of x of t is less than m, means the input is bounded. The output yt is a summation of infinite values from infinity minus infinity to t. So when we sum infinite values, even though xt is bounded, for infinite values when we sum, the output may go to infinity. So there is no guarantee that the system will be stable. Now consider yn given by summation m equal to 0 to 10 x of m. And again let us say that xn is bounded, it is less than m. But there are only 11 values to be summed. So yn will be always less than 11 times m. So the output will also be bounded and the system is Bibo stable. Now consider the integration like this. Integration t minus 3 to t x of tau d tau. Now in this case we are considering the finite interval of 3 units t minus 3 to t, and if x of t is bounded less than m, y of t will also be less than m, so it will also be bounded. So this is a Bibo stable system. Consider yn is sine of xn. If xn is bounded, what will be yn? Yn is sine of xn, so it will be less than 1 because sine is always less than 1. So the system is Bibo stable. So every sine, cosine function will always be Bibo stable. Now let us consider the physical significance of stability. The stable system is of practical importance. It is of practical value because unless the output is having some finite value, the implementation of the system is not possible. If the system is unstable, what will happen? The extraneous noise or even thermal noise that may be present in the environment, it will allow the system to become unstable and the system output may become infinite. So in that case, it is of no use. So the system will have to be always stable. Now, how to ensure that the system is stable? It can be ensured from the characteristic roots. So, what is a characteristic polynomial? Characteristic polynomial is the denominator polynomial of your transfer function of the system. And for this denominator polynomial, you are supposed to find the roots. If these roots are on the left hand side of imaginary axis in S domain, we say that the system is stable. And if these roots of the polynomial or characteristic equation are within the unit circle in Z domain, we say that the system is stable. So we'll come to the Z domain, that is Z transform, in the further lectures. But you try to remember this, that there is a possibility of finding out the stability of the system from the characteristic roots. So you will have to find out what is the characteristic equation, that is the denominator polynomial of the transfer function, find its roots and find where the roots lie. So using pen and paper you can find out whether the system is stable or not before it is actually implemented. That is important. Now consider the interconnection system as interconnection of operators. So let us say that the system yt is given by 1/3 of xt plus x of t minus 1 plus x of t minus 2. And on similar lines, yn, that is a discrete time system, is represented on similar lines using this equation. Now let us represent S as the block representing the delay of one time unit or one time sample. So in that case, can we represent it in the form of a block diagram? We can represent this system as yn is equal to 1/3 of xn. Let us say this is xn. So I take 1/3 of xn, that is just multiply the input by 1 by 3. Then allow one time unit delay, that is you get x of n minus 1, multiplied again by 1 by 3 to get 1 by 3 x of n minus 1. Again apply a delay of one time unit, so you get x of n minus 2. Again multiplied by 1 by 3 and add up all these to generate yn. So this becomes the system block schematic to generate yn. Now here this S represents a block which is a time unit, delay for time, one time unit or one time sample. One time sample in case of discrete time systems. Now consider this particular example. In this case, y of n minus 1 is also inward. So how you get yn? For yn, we will have to take xn plus half of xn minus 1. So when you introduce a delay of 1 unit, I get x of n minus 1. You multiply it by 1 by 2. So you get half of x of n minus 1. Then this yn is also delayed by one sample to get the previous y sample. So multiplied by minus 1 by 3. So minus 1 by 3 y of n minus 1 and interconnect, add it to this previous xn and half of xn minus 1 and you will generate yn. Now in this case the system includes the current sample and the previous sample and also the previous output sample. So the system is causal and it is also stable if the input is bounded. Consider the series interconnection of the two systems. Suppose let us say we have x1t, this is one system, and this is x2t, h2t, and if we connect it in series, what will happen? When you interconnect the two systems in series with their impulse responses represented as h1t and h2t, then the combined system, that is the interconnected system, series interconnected system, will have impulse response given by h1t convolved with h2t. That is important. So we conclude that when the two systems are cascaded or connected in series, the impulse response of the cascaded system is the convolution of impulse responses of the two systems. So firstly convolve the two impulse responses and then find the output yt as convolution of the input and the effective impulse response. Now let us consider the parallel interconnection. The two systems are connected in parallel with the impulse responses given by h1t and h2t. Now in this case, how the output yn will be calculated, yt will be calculated? We'll have to find out xt convolved with h1t and add x1t convolved with h2t to it to generate y of t. Right. So if it is parallel interconnection, you have to add up the impulse response result of convolution of impulse response of the individual systems with the input x of t. Now parallel interconnection of DT systems on similar lines, yn can be calculated of xn convolved with h1n and xn convolved with h2n and then add up the two to generate yn. Here the integration is, the summation is written as minus infinity to infinity x of m h1 of n minus m. So this is a standard formula for convolution. Now this is the interconnection of four systems. Two systems are connected in series, two systems are connected in series and then they are connected in parallel. So what will be the effective impulse response of the system? Effective impulse response of the system, let us represent it as h double dash t. It will be equal to sorry, it will be equal to h1t convolved with h2t plus h1t convolved with h3t. Thank you.